What if the heart of a black hole isn't a point of infinite density, but a quantum bounce, a tiny moment when collapse reverses and matter springs back? The standard teaching says, inside a black hole, gravity crushes everything to a singularity, a place where physics breaks and time ends. Yet a growing chorus of theoretical ideas says the quantum nature of spacetime itself could stiffen like a spring at extreme density, turning a crush into a rebound. If true, black holes would be not only cosmic sinks, but potential engines of new regions of reality. The question isn't just arcane math. It touches the fate of information, the origin of possible baby universes, and what happens when gravity partners with quantum rules. So, could the mysterious quantum gravity bounce actually prevent the singularity and rewrite the black hole's ending? And if such a bounce exists, what would it look like to an outside observer looking down from the light-filled universe we inhabit? Open the door, and let's walk through. To understand why this idea matters, we need the old map. For most of the 20th century, general relativity painted black holes as simple, absolute endpoints. Collapse drives density to infinity, curvature explodes, and something called a singularity sits at the core, hidden behind an event horizon. The mathematics that worked so well elsewhere began to trip at those extremes, and physicists began to wonder if a deeper theory would rescue us. The relentless logic of Penrose and Hawking showed that under broad conditions, singularities were inevitable if classical gravity held sway. That was the stage, a universe governed by smooth spacetime, where matter could be squeezed only until reality let go. Then came quantum ideas that spacetime might be discrete, that geometry has texture, that gravity could switch from a crush to a repulsion at the smallest scales. Loop quantum gravity, among others, suggested precisely that kind of repulsion. As density approaches a Planckian limit, quantum geometry resists further compression. In cosmology, that led to the famous idea of a big bounce instead of a big bang. The leap was natural. If quantum gravity can avert a singular beginning of the universe, could it do the same inside an imploding star? The door opened. But the inside of a black hole is a different room, filled with strong anisotropy and horizons. It's not magic. It's the microstructure of spacetime resisting unlimited shrinkage. Inside the black hole, the interior can be modeled as a highly symmetric, nearly cosmological space. There, the same quantum corrections that avert a big crunch in the early universe can avert a singular crunch here. The matter doesn't vanish. It rebounds, hitting a maximum density and then driving outward. In some pictures, this rebound creates a Planck star-like core that hovers for a fleeting moment before expanding. In others, the interior connects to a white hole-like phase, potentially birthing a new region beyond what we would call the event horizon. The breadth of possibilities matters less than the shared mechanism. Quantum geometry provides a repulsive pressure at extreme density, turning collapse into bounce rather than catastrophe. The how is the interplay of spin networks, holonomy corrections, and the statistical behavior of quantum geometry. The what is a finite relativistic rebound that preserves information in a consistent, if quantum, clock. Observationally, any external signature, gravitational wave echoes, delayed bursts, unusual lensing, would be faint and tangled, but not impossible to imagine in principle. If the affordable, testable ideas are right, we would be watching a choreography where collapse and expansion trade places inside the same space-time stage, hidden behind a horizon that itself acts like a quiet witness. Why should this matter beyond a clever speculation? If singularities disappear, black holes could become laboratories where quantum gravity operates in the wild. Information puzzles tied to horizons might loosen if interior evolution can be followed through a bounce rather than lost to a point. A successful bounce would suggest a continuity between interiors and exteriors that challenges strict cosmic censorship, offering a path for information to influence the outside world in subtle ways. It also strengthens the bridge between cosmology and black hole physics. The same quantum geometry that prevents a crunch at the birth of a universe might do the same inside a collapsed star, hinting that our universe could be born from the death of an ancient black hole in an earlier cycle. The practical upshot is not immediate technology but a shifting worldview. Space and time become pieces of a quantum tapestry whose texture matters at Planck scales and whose whispers could reach us through gravitational waves, exotic transients, or the long, slow drama of black hole mergers. If real, the bounce transforms black holes from simple endpoints into potential engines of new spacetime, a twist in the cosmic story that connects every star with every other through the thread of quantum gravity. From the first picture of a point of infinite gravity to the possibility of a quantum bounce, we've walked a path from inevitability to a door that might open in the presence of quantum geometry. The singular endpoint can be replaced by a turning point, a moment when density reaches a ceiling and the inner universe starts to unfold again. In that view, black holes become not just sinks for matter and information, but gateways to deeper layers of reality, where space and time are not rigid backgrounds but dynamic bouncing stages. The mystery remains, but the direction is clear. Quantum gravity is not an ornament on general relativity. It is its next chapter, responsible for endings that tire of ending and beginnings that refuse to end. The cosmos keeps surprising us by turning the crush of gravity into the spark of a rebirth. If you want more journeys to the edge of physics, subscribe.